Okay, thank you. Thank you for introducing, and I'd like to thank the organizers for giving me this chance to talk here. Very nice conference. I'm going to talk about complete orthogonal arrays of strength 3. This is based on joint work with Sasha Gabriuk from Shimane University in Japan. Okay, so around 1980s, Ryuzaburo Noda, who is a Japanese mathematician, obtained the following results about the some full or partial classification of complete orthogonal arrays. This is taken from the handbook of combinatorial designs. His theorem is about the classification for strength 3, 4, or 5. The strength 3 case, there are two parameter set here, this one or this one. I will explain the later, but the first one is the binary case and the second one is the Q-array case. And the strength 4, there are three cases. The first two orthogonal arrays are completely classified, and namely these parameters are uniquely determined from their parameters. And the third one is one parameter family. And the strength 5 case, this case was completely classified. In this talk, I'm going to focus on the strength 3 and the second case. In this case, Noda obtains a result about this parameter Q is even. And my main result in this talk is if Q is larger than 2, Q must be a multiple of 4. And by the way, the third case in strength 4, I and my co-author, Sasha Gabriuk and Janos Fidari, we obtained the non-existence result of this case. And this was ruled out in 2020 and already appeared journal Combinatorica. In this talk, I'm going to use the theory of association schemes to use restriction parameters. And this is the rough contents of my talk. I will briefly review the association schemes and Q-polynomial schemes and the design theory in its space. And after that, I will introduce or show some result about the theory for Hamming schemes. And namely, this is the design Hamming schemes is same as the orthogonal arrays. And we discuss its completeness or tight conditions. And finally, I would like to give a sketch of our result, proof of our result. Okay, so next speaker, Bill, will talk about this in details. I want to skip some parts, but at least I want to define the symmetric association schemes. It is a pair finite set X and binary relations Ri. And this pair is said to be a symmetric association schemes if the following 4 conditions satisfies. Here AI is the adjacency matrix of the graph whose vertex set is X, the whose edge set is the binary relation Ri. The first condition in symmetric schemes is the A sub 0 is the identity matrix, and the second condition is the summation of all the adjacency matrices is equal to the all ones matrix, which is denoted by J. And the third condition is about symmetric conditions. Each adjacency matrix is symmetric. This means each graph is undirected graph. And the fourth condition is very important in the theory of association schemes. For any ijk, there exists some non-negative integers pijk, such that the aiij can be written as a linear combination of ak, and whose coefficient is equal to pijk. If we consider the vector space A spanned by all the adjacent matrices AI over real number field, this forms the commutative algebra from the fourth condition in the previous slide. And this algebra has a primitive idempotent EI. They are same as the orthogonal projection of the maximal common eigenspaces of the adjacency matrices. In this algebra, we have two important parameters. One is the prime parameters denoted by Qijk. This algebra is closed under the entry-wise multiplication. So we may define Qijk from this equation. If we consider the entry-wise product EI and EJ, this can be written as a linear combination of EK because EK also forms the basis of the vector space A. So we can define this coefficient Qijk. This is, and the second one is the eigenmatrix, second eigenmatrix. And these two matrices are the basis of this vector space. So there is a change of basis matrices denoted by P or Q. And if we write EI as a summation of AJ, and if we correct its coefficient of Qji, we call the matrix Q the second eigenmatrix, and the second eigenmatrix and the prime parameters Qijk play very important role in this talk. And one of the important class of symmetrical association schemes is a Q-polynomial. And the scheme is said to be a Q-polynomial with respect to some ordering of primitive idempotents. If the Klein matrix defined by this one, Q1jk, whose jk entry is equal to Q1jk, is a tridiagonal matrix with non-zero super diagonal entries and sub-diagonal entries. Both entries are non-zero. And the design can be defined in the Q-polynomial association schemes. This is the work by Delsart around 1970. Let X be Q-polynomial schemes, and a subset C of the vertex set X is said to be a T-design if its characteristic Klein vector chi satisfies this equation. EI chi is equal to 0 Klein vectors for any I from 1 to T. And the result considers a general theory of T-design Q-polynomial schemes. And if we restrict the Q-polynomial schemes to the Hamming schemes or Johnson schemes, so we can define we have a T-design in those spaces, and they coincide with the orthogonal array in Hamming schemes and classical T-designs in Johnson schemes. And in this talk, we deal with the Hamming schemes and its designs, namely orthogonal arrays. So here is the definition of Hamming association scheme. Its vertex set is the direct product of Q element sets, and the binary relations on the set X can be determined from the Hamming distance. The Hamming distance is the the number of indices I with xi is not equal to yi for two vectors being x. The Hamming scheme is the vertex set X, pair X, and the binary relations Ri. This is indeed symmetrical association schemes. Moreover, Q-polynomial association schemes whose first and second eigenmatrix can be determined from so-called Kirchhoff polynomial and orthogonal polynomial. And if we consider the T-design in these Hamming association schemes, this is same as the orthogonal array. In this talk, we denote it by OA, NNQT, or OA, N over Q2T, TNQ. Okay, so I think many of you already know the definition of orthogonal array, but I want to define it. It's an n times n matrix M with entries from 0 to Q minus 1, such that in any n times T submatrix of M, all possible row vectors of length T occurs exactly the same times. In this case, that value is equal to Q to the T over N. Okay, here is the simple example of the orthogonal array. This example has parameters 8, 4, 3, 2. So 8, 4 means this matrix is the 8 times 4 matrix, and Q is 2. So this matrix has two symbols. And in this case, the strength T is 3. 3 means if we consider any 8 times 3 submatrix, for example, if we restrict the columns to the first, second, and third columns, so we have here A times 3 submatrix. And if you look at all the rows of this submatrix, then we can easily directly check the all possible three vectors, all possible the vectors of length 3 with two symbols appears exactly the same times. In this case, the repetition number is 1 in this case. Also, if we restrict the columns, the first, second, fourth, or first, third, fourth, or and so on, we can check each sub S times 3 submatrix have the same property. So we can conclude this matrix is the orthogonal array with these parameters. And in the theoretical design, it's very important to find designs with as small as possible vertices. This means finding the nice lower bound is very important. In the Hamming schemes case or orthogonal arrays case, Rao obtains the following lower bounds depending on the parity of strength T. If the strength T is even, the number of the rows of orthogonal arrays is bounded below by this value. And if T is odd, the number of rows of orthogonal arrays is bounded below by this value. And T design of orthogonal array is said to be tight or complete if it achieves this inequality. If equality holds, we call the designs are tight or orthogonal array are complete. So now we focus on the when tight design exists, and I want to show some non-existence result for tight design or complete orthogonal array. And to do so, we need the following two concepts. First one is degree set, and the second one is distance set or degree. Degree set is defined for subset C in the Hamming schemes, and this set is S denoted by S of C, which consists of the Hamming distances for any distinct vectors being in the subset C. And if its size is equal to S, we call the subset C an S distance set. So because there are the S distance set between any two distinct vectors in C, and also we call S degree. Okay, so the result obtains a following very nice result in Hamming schemes. Let's achieve a tight T design. Then C is this value distance set, and if T is odd, if strength T is odd, the length N appears as the Hamming distances in the subset C, and also this equality holds. This equation is very important in order to study the tight design or complete orthogonal array. This equation says if we consider the Hamming distance in the subset C, it is the zeroth of this polynomial. So this polynomial is the summation of the Kirchhoff polynomial. And here we have some parameter epsilon. Epsilon is equal to 0 if T is even, and equal to 1 if T is odd. If we use this theorem, we can show non-existence result of tight even designs. Okay, so namely, if there exists a type 2e designs, so this polynomial must have the distinct integral zeros in this interval from 1 to n. Actually, this yields a non-existence result for many cases. The first case is shown by Noda, 1979. For E is equal to 2 and Q is not equal to 6. This means type 4 designs in Hamming schemes H and Q, where Q is not equal to 6. Noda completed the classification for this case. So by the way, so the case Q being 6, in this case was ruled out by our result in 2020. And after that, Hong result obtains a non-existence result for these case type 2E design and the QRA case where E is at least 3 and Q is also at least 3. And 1994, Mikaji and Kageyama shows the non-existence for type 6 design binary case and some partial classification, non-existence result, type 8, 10, 12 designs in binary case, but in this case, length is at most 2 to 10. And also I want to mention the existence about the type designs. So there are so many type 2 designs in Hamming schemes, namely, there are so many complete orthogonal array of length 2. So this is something similar to the Johnson schemes case, I mean, and there are so many symmetric designs, so this result corresponds to such phenomena, I think. So how about the tight odd designs in Hamming schemes? And if we have a tight odd designs, then if we consider the contraction of that orthogonal array, namely if we correct the rows of the orthogonal array, whose first entry is equal to fix the symbol I, and then delete this symbol, this C sub I is a type 2E design in Hn-1Q. Okay, so length is 1 smaller than the original one, and also length is 1 smaller than the original one. So using the non-existence result for derived type even designs, we also have a non-existence result of an original type of design. But the type 3 design case, if its contraction is a type 2 designs, and type 2, as I said, there are so many type 2 designs, so we don't have any non-existence result, but the Noda obtains the following result. He showed type 3 designs have a parameter, one of the following. The first case is Q is 2 and the number of rows equals 2 times n. And the second case is the number of symbol Q is even and the length n is Q plus 2 and the number of rows is Q. And as you can guess, and the first case is related to Hadamard matrix and actually equivalent to the existence of the first one. Its existence is equivalent to that of a Hadamard matrix of order n. So in this sense, we cannot do the first case. And the second case, this complete orthogonal array of string 3 exists if Q is a power over 2. And also we can easily show that each contraction is a complete set of mutually orthogonal latent squares of order Q. And such sets complete modes exist. That is conjecture that the existence of complete set of modes of order Q is the Q being power prime. So in this case, Noda already showed Q is even. So I think the second case exists if and only if Q is a power 2. But this is still a conjecture. And in this talk, I want to show if Q is larger than 2, and Q must be a multiple of 4. And so how about Noda obtains his result? How did he get his result? He used the Delsart theory like this. So Delsart theory is about the T design with degree S if T is close to 2S. And actually, Delsart shows the strength T is at most twice S. And if T is at least 2S minus 2, then this pair vertex set C, this is the T design C, and the SI is a binary relation defined on C, which is determined from the Hamming distance alpha I, where we assumed C has the Hamming distance alpha 1 to alpha S. His Delsart result is this pair forms a Q-polynomial association scheme of S classes. If we apply this general result to our case, namely type 3 designs, in this case, degree must be 2, and this case satisfies this inequality, T is at least 2S minus 2, so we have a symmetric two-class association schemes, namely this object is same as the strong regular graphs, and Noda investigated its parameters, namely the intersection numbers or the eigenvalues or the multiplicity of eigenvalues of corresponding SRGs. Then he arrived at his conclusion, namely this result. Okay, so this is a summary for this work, and I want to show this conditions for the second case. So in order to show our main result, so we do the following two. And the first, we want to show two-class schemes or strong regular class has a three-class fission association schemes, namely we construct another association scheme of three class. And then we calculate calculate so-called triple intersection numbers of the resulting three-class schemes. Then we arrive at our main result. Okay, so next I want to explain the first part of our main result. So how to obtain the three-class schemes is, this is somehow complicated, but okay, we are given a C, which is a type 3 design in this Hamming schemes, length n is equal to q plus 2. And we consider we delete just one coordinate of the every vectors being in C. We denote it by C tilde, that set, and also we use the CI. This is the contraction of the obtained from the original type 3 designs. And we can easily check using the result or Noda's result. And this set, the degree set of C tilde forms these three values, namely this C tilde is a 3 distance set, and using 3 Hamming distances, we can define the binary relations on the set C tilde like this. Now our claim is this pair C tilde and the binary relations defined from the Hamming distances form the symmetric association schemes of three classes. In this case, the C tilde is in Hamming scheme HQ plus 1Q, and this is also forms a 2 design, namely orthogonal array of strength 2, and also this has a degree 3. So this example satisfies that T is equal to 2S minus 4. So this means that general Delsart theory does not guarantee this our pair form an association scheme. So we need to do something in this case. The idea of this proof of this result is as follows. And not only C tilde, but also each CI forms a 2 design in the same Hamming scheme. Also, we consider the number of distances between i's contraction Ci and j's contraction Cj, and the number of distances between Ci and Cj is equal to 2. In this case, if we set Ti as the strength of the Ci and each Ti and Sij satisfies this inequality, Tj is at least Sij plus Sjk minus 2, and both sides are equal to 2. So actually, equality holds in this case, but we have this inequality for any ijk. And if we have a set of designs, and if these designs satisfies this inequality, we can show, I already obtained some result about this case, and each union of designs forms a so-called coherent configuration, I didn't define this object, but this is a generalization of association schemes. I obtained this result maybe 10 years ago, the paper in JCTA. And now we have we can construct a coherent configuration from type 3 design Hamming schemes. And also this association, coherent configuration has so-called uniform property. Roughly speaking, any union of the fibers forms, or again, a coherent configuration. And this property is extensively studied by the Van Dam and the next speaker, Belmonte and Michichak in 2013's JCTA's papers. And if we use their result, our coherent configuration forms also association schemes. So this is the idea of this proof.
Sorry to interrupt. Sorry to interrupt. You have 3.5 minutes.
Yes. And if we calculate the symmetrical association schemes, its parameters, we can show that this is the Q-polynomial schemes with the following parameters. Okay, so now move on to the second topic about the triple intersection numbers. So association schemes is calculating the double intersection numbers, namely the number of common neighbors from two distinct vertices, and how about the three distinct vertices? That is about the triple intersection numbers. So if we consider the three vertices U, V, W, and if we consider the common neighbors from U to the I's relations, from V to the J's relations, from W with K's relations, so number of common neighbors is said to be a triple intersection numbers. So in general, there are so many triple intersection numbers in association schemes. And about the triple intersection numbers, we have a nice result about this related to the Klein parameters. If Klein parameter vanishes, then we have this kind of linear equation of triple intersection numbers, where small qijk is Klein parameters and the large capital Q is the entry of second eigenmatrix. So now we have a system of linear equations whose unknowns are triple intersection numbers, and solving this linear equations is of course, some information about the triple intersection numbers. And if we are lucky, sometimes it contradicts and integrality for triple intersection numbers. Okay, so now I want to show sketch of our proof. In this case, just calculating the sum intersection numbers from three vertices U, V, W, whose relations are R2, and there exist such triangles because Q minus 2 is positive, so there exist such triangles. That's solving the linear equations of triple intersection numbers. Then some values is equal to this one for over Q2 minus Q. And of course, this is also integer. And we know Q is also even. So Q for over Q is also integer. So this is our contribution to this case. Okay, so with the node as a result, we have the following theorem. And this is the very important open problem, I think. Is it true that Q is a power 2? Okay, so this concludes all my talk. Thank you for your attention.